Hi, welcome back to CMSC 82080. Today we'll be talking about velocities and transformations related to velocities. Before we dive into velocities, we need to talk a little bit about mathematics before. So let's start with manifold. What is a manifold? A manifold of a dimension m is a set M which is homeomorphic to R. So you might be asking what is homeomorphic or what does homeomorphism mean? So we'll come to that in a little bit. A homeomorphism is a map F which takes you from set M to set N such that F and F inverse are both continuous. So a cartoon representation of this is shown on the right hand side in this figure. A function F which again maps you from M to set N is continuous if for each open subset of V which belongs to N, the set F inverse V is an open subset of M. So take a moment to think about what that is. Also note that a function can be both bijective and continuous without it actually being a homeomorphism. Why is this all important? We'll come to that in a little bit. So if you don't understand something in this slide, pause the video, go read about it from Wikipedia or any other source, and come right back. So let's dive right in and talk about rotation on a plane. Consider an XY plane as shown in the figure, and we have an origin which is shown in the center of the unit circle being shown in red, and any point on this can be thought of as an imaginary number as shown in the figure, and it can be represented by e power I theta, where I is the imaginary number root of -1. This can also be represented as a rotation matrix, cosine theta minus sine theta, cosine theta, and can also be represented as a complex number exponential form as given here, which is z of theta is cos theta plus I sine theta or e power I theta. So you might be wondering, how can this be shown? This can be simply shown by getting a series expansion of e power I theta and separating the even and odd terms. That's shown right here. The exponential function maps the tangent vector at 1 onto the circle of radius 1 or unity circle. The line can be also viewed as a tangent to the circle group of SO2 because it's a 2D rotation matrix with the identity element being e power I0, which is corresponding to identity rotation matrix or zero rotation angle in 2D. Next, we need to talk about what is an exponential map onto SO3. So a cartoonish representation of this is shown on the right. So we have multiple properties which we will be talking about. The first property being exponential of 3 by 3 skew-symmetric matrices are rotation matrix. So put it in a more mathematical formal way, it's as shown in the next line. For all omega, which belongs to R3, there exists a rotation matrix R, which belongs to SO3, such that R is exponentiation of this omega hat, where omega hat is the skew symmetric component of omega, where omega is a vector 3 by 1. The property 2 is that the exponential map is surjective onto SO3. Surjective here means that it's a many-to-one mapping. It's not a unique one-to-one mapping. So more mathematically, it's for all rotation matrices which belongs to SO3, there exists a vector omega belonging to R3 such that omega hat can be taken as the matrix log of the rotation matrix, which is exactly the same as property 1, just inverted. So a little bit of definition here. The set of all 3 by 3 skew-symmetric matrices is called a Lie algebra, denoted by little SO3 or script SO3 as shown here, for the Lie group capital SO3 or special orthogonal of group 3. So now we need to talk about the rotation about an axis. Consider the XYZ frame as shown here. Consider a vector R shown in bold red, and we will be rotating by an angle theta around this axis in an anticlockwise direction. And the vector components of this R are Rx, Ry, and Rz. And the angles with respect to x-axis and z-axis is shown as alpha and beta here. So this rotation about an axis can be found by a formula called Rodriguez formula, and it's given here. So it's the rotation matrix obtained by a vector r rotating about a vector r in anticlockwise direction by an angle theta is given by an identity matrix of the same size. In this case, it's 3 by 3 into cosine theta plus r transpose into 1 minus cos theta plus r hat into sine theta. You might be thinking, what is exactly theta? How do you get it? And what is r hat? That's going to be the next point. So cosine theta is obtained as the trace of the rotation matrix r minus 1 divided by 2, and r hat is given by this formula here. The inverse of the cos already restrict the interval to 0 to pi, making it a 1-to-1 mapping with respect to r. So that's a good thing. So it's super intuitive. So inversion is 1-to-1, and we're good to go. So next we need to talk about how we take an exponential of a 3 by 3 skew symmetric matrix. The matrix exponential of a function on square matrices is given as follows. It's analogous to exponentiating a normal number, but in this case, it's all matrices, where a square is a into a and so on. So we can write a hat in terms of a unit vector and angle, as shown here. And we take a hat is equal to u hat into theta and plug it back into the equation 1, and we would get something like this. And it's clear that u hat power 4 is minus u hat square, and u hat power 5 is u hat, and so on. Pause this video, think about it for a moment. Why is it so? It's a fairly obvious thing. And now grouping the even and odd terms together, we get the formula on the bottom, which is in turn can be written as follows, and it's basically the Rodriguez formula. We just derive the Rodriguez formula by taking the definition of exponentiation. And we want to now verify that indeed exponentiation of u hat theta is actually a rotation matrix. If you recall, rotation matrix is any element of SO3 and is defined by the following properties. So SO3 is defined as any element R which belongs to 3 by 3 real number set, such that R transpose R is R transpose is identity, and the determinant of R is +1. So we discussed this before. The reason why we choose determinant of R as +1 is because we choose a right-handed coordinate frame system. And let's exponentiate the u hat theta and take the inverse of it. It's clearly we can find that exponentiation of u hat theta, the inverse of it is the transpose of the matrix, which is the first property for a rotation matrix. Now we need to show that the determinant is indeed +1. This can be simply shown by taking exponentiation of u hat theta transpose into exponentiation of u hat. And we can take the determinant of both sides, and it's clear that the answer is 1. So determinant of A and determinant of A transpose is the same. So the determinant has to be +1 because they both have to be either -1 or +1. In this case, because you've chosen one of them to be +1, it has to be +1. So this means that any exponential of the form u hat theta with norm of u being 1, that's the representation why we used u hat, is a rotation matrix. So the opposite is also true, and it can be simply shown by a constructive proof, which I'm going to leave it as a homework exercise. Now, what's the physical interpretation of all this? Consider a rotation of an angle d theta around an axis u as shown here. So simply by definition, we can write the angular velocity as u d theta by dt. Assume that d theta is a very small angle and dt is a very small amount of time of the order of limit tending to 0. So now we can exponentiate u hat d theta, and we can simply apply Rodriguez formula, and just by writing everything out, we would get this equation. That's the physical intuition of what is happening here. So next we want to talk about the derivative of a rotation matrix, because this is all building up to how we transform velocities among different coordinate frames. So as stated before, we want to find the derivative of a rotation matrix. We start with the well-known fact that R transpose R is identity. Note that I have put an R as an R of t here, signifying that the rotation matrix is changing with respect to time. And we differentiate this by using the product rule, which is R transpose R dot plus R dot transpose R is equal to 0 because the derivative of identity is 0. And now we can notate this or signify this as R transpose R dot as S transpose, or in other words, R dot transpose R as S. Thing to note here is that for any skew symmetric matrix, A transpose is minus A. We know that S is a skew symmetric matrix, so this would satisfy the same properties. So just as a side note, a cross product between two vectors can be written as a skew symmetric matrix of the first vector multiplied by the second vector. So the skew symmetric operator takes a vector and converts it into a matrix, and in this way you can convert a cross product into a matrix times a vector. Why is that useful? We'll come to that later. So but just remember this for now. So the idea here is that we want to find the angular velocity in the setup as shown. So consider a world frame A as shown in the figure in red, and consider a rock or a rigid body like the one we had in the previous slides or the previous lectures, and you have a point P on this rock in the coordinate frame system B. We want to find the velocity of the point in frame A given the velocity of the point in frame B, or vice versa. That is, transform between the velocities of the point between two coordinate frames A and B, or B and A. So we start off with the well-known fact that Q is equal to R into P. In this case, Q is a time variable vector because the rotation matrix or the pose of the stone is varying with respect to time. So we are given the angular velocities in the body fixed frame B, which is the blue frame, and we want to find the angular velocities in the world fixed frame A, which is the red frame. If you remember, it's shown here. So in essence, we want to find Q dot, which is R dot into P. So this can be written in as from the previous slides again as the skew symmetric matrix of an omega vector into R into P, like we just discussed in the previous slides. If you don't understand this, please go back to the previous slides and come back to the slide again. So if omega t is the angular velocity with respect to the reference frame, with the rotation R of t being a time variable rotation matrix at being fixed at the time t, from mechanics we know that Q dot is omega cross R into P, which is basically the same thing as what we wrote in the previous equation. We know that the skew symmetric matrix represents a cross product, hence Q dot is omega cross R into P, or S of omega into R into P. Now we want to talk about transforming the velocity of a point, which was the title of this talk or the lecture. So consider the same thing as before. We have a frame A shown in red and a frame B which is fixed to the rock or the rigid body as shown in blue, dark blue here. The light blue points are related to the vectors corresponding to the point of which we want to transform. So from the previous lectures, we know that a point in frame A can be denoted or obtained from a point in frame B as follows, which is rotation matrix which takes you from frame B to A multiplied by the point in frame B plus origin or translation which takes you from frame B to A. Now to find the velocity, we just have to differentiate this equation, and this can be seen as follows. And converting R dot as skew symmetric into rotation matrix and converting skew symmetric as a cross product, we get this equation. So just pause the video for a minute and look at the equation. It's fairly obvious. Now assume that the point P is fixed in frame B, which means that the rotation component into P dot becomes 0, and that is shown in this equation here. Now if the rigid body only rotates, that is the translation is 0, the O dot value will be 0 and the final answer will be something like this. Now again, we are visiting the velocity of a point again, and it's the same thing with origin being 0, and that's the last equation in the previous slide. So now You can multiply both sides by R, which takes you from frame B to A transpose, and you would get the equation shown on the bottom here. So the left-hand side is the velocity in the body fixed frame. The part in the green encodes the angular velocity in the body fixed frame. And we can rewrite PB in the inertial frame as R, which RBA transpose into PBA. And this gives you the following equation shown in the last line here. The left-hand side is the velocity in the inertial frame, and the thing in the yellow box encodes the angular velocity in the inertial frame. So this is how you would convert from velocity in body fixed frame to the angular velocity in body fixed frame, or velocity in the inertial frame to the angular velocity in the inertial frame. Please remember these equations. Uh, this is pretty important. Now again, I'm rewriting the same equation again. So the left-hand side is the velocity in body fixed frame, and the thing in the green box encodes the angular velocity in the body fixed frame. And same thing here. And the left-hand side is the velocity in inertial frame, and the thing in the blue box encodes angular velocity in the inertial frame. One thing to note is that R transpose R dot is omega hat B, and R dot R transpose is omega hat S. Both of these are skew symmetric matrices, which basically talk about the angular velocity in body fixed frame with respect to inertial frame in body frame for omega hat B, and angular velocity in body fixed frame with respect to inertial frame in inertial frame for omega hat S. Pause the video for a second and take a moment to digest those words. This comes from the 1994 paper by Murray, that it's very similar to the Taylor series expansion or first order expansion in dynamics, which is shown here. So the angular velocity in body fixed frame would be obtained as R into omega hat B, that is shown here, and same thing for the inertial frame. Now we want to talk about angular velocities and Euler angles. Assume ZXY Euler angle parameterization. For the quadrotor, you will have to determine the relation between the angular velocities and the orientation to determine the attitude dynamic model, which is shown here. So the idea here is that even by using Euler angle representation, we can uh, transform between the various coordinate frames the velocities obtained. The reason why this is important is because you might be calculating the velocities in an inertial frame or in a body fixed frame, and you might want to transform it vice versa for pose estimation, which we'll be talking about in the later lectures. So now we want to again come back to the key point of this lecture, which is transforming velocities. Consider the setup shown here. We have the same frame A, and we have two frames B and C on the rock. They're rigidly rotated, attached to this rock, and all the notations are very clear. And both the points about frames B and C are rotated at an angular velocity omega B and omega C respectively. That is written by this equation, which is RCB is rotation matrix C into R, which takes you from CB to C, or represented in C. And we know that because they're rigidly attached to each other, the angular velocities omega C and omega B are exactly the same. And differentiating the equation from the previous slides, we get PB dot as PC dot plus skew symmetric matrix of omega C into RCB, or which in turn can be written as PC dot minus skew symmetric of RCB into omega C, because we know that swapping the order of the vectors in the cross product negates the sign. This could be compressed into a matrix equation as shown. And to summarize, these are the equations which are written again. And pause the video for a second and go through these equations. And the final summary is the one shown in red here, which is P dot of represented in B, omega which is represented in B is given by this matrix into the velocity in frame C and omega in frame C. Now let's talk, or let's rewind what we studied about homogeneous transformations for a second. If you do not remember any of these equations, please go back to the previous lectures and go through the homogeneous transformations. So the homogeneous transformation matrix represents the rigid body transformation and is characterized by a 4 by 4 matrix where the first 3 by 3 is a rotation matrix and the last column, first three rows are basically the translation vector and the bottom row is 0, 0, 0, 1. And homogeneous representation of any vector is basically appending 1 to the vector, in effect making it a 4 by 1 vector, and that is shown here. We want to take the derivative of homogeneous transformation matrix. For a rotation matrix, we know that the skew-symmetric matrix is defined as R dot into R transpose. Similarly, for a homogeneous transformation matrix, we can define H dot as sum SH of t into H of t, which the equation of which is given here. It's very similar to the one we had for rotation matrix, but it's a little bit more complicated because of the coupling between translation vector and the rotation matrix. And indeed, we can represent SH of t as, again, a 4 by 4 vector, where it's represented by omega hat and v, and which is denoted here by chi hat. This this matrix 4 by 4 is also called as twist in general terms. Now we want to talk a little bit about exponential map onto SC3. So this is analogous to what we had for SO3, but in this case it's SC3 because it's dealing with both the whole Euclidean space, that is the rotation and the translation. So exponentials of a 4 by 4 matrix of the transformation of the time homogeneous is represented by chi hat, which is omega hat v 0, 0. Note that the difference here is that it's 0, 0 and not 0, 1. So more mathematically put, for any chi which belongs to a 6 by 6 real number space, there exists a homogeneous transformation matrix which belongs to SE3 such that you can take the exponentiation of the chi hat and we would get back the homogeneous transformation matrix. Note that this is SE3 and not SE6, though the matrix is 6 by 6. The reason why this is 3 by 3 is because we are dealing with 3 degrees of freedom here. The property 2 is that the exponential map is surjective onto SE3, which is exactly the same thing as what we discussed before. This is a many-to-one mapping, and this property 2 is basically the inverse of property 1. That is, for all homogeneous transformation matrices which belong to SE3, there always exists a chi which belongs to real number space 6 by 6, such that chi hat is the matrix log of the homogeneous transformation H. Note that this is just a sneak preview. Please feel free to read about this if you want to know more. Wikipedia is an amazing source to learn about SE3. This is one of the oldest study topics in mathematics. So again, by definition, the set of all 4 by 4 matrices that are of this type is a Lie algebra and is denoted by script SE3 or little SE3 for the Lie group, capital SE3 or special. Now we'll have to talk about the derivative of a homogeneous transformation. This figure is exactly the same we were using in the previous slides. Consider a constant vector p with the properties shown here. Here capital Q or capital P represents the homogenized version of P and Q as we had in the previous slides. So Q of T is basically the homogeneous transformation B, which takes you from B to A into P. And if we differentiate this, we just directly get the twist matrix. And basically capital P is represented in the body frame, or in this case, the frame of the rock, in our case, it would be the frame of the quadrotor. And homogeneous transformation transforms the vector into the inertial frame or the world frame from the body frame. So this is exactly the same as what we had for rotations. So please pause the video for a second and see how we transform between velocities among body fixed frame and inertial frames. So it's super intuitive, and ask questions if you don't understand in class. So again, writing the same equations. So we had velocity of a point, which we could derive as follows. I am not going to go through it because it follows exactly the same derivation as before and is super intuitive to follow. And it's the same thing as what we did for rotation matrix, just the difference being this is done for the whole homogeneous transformation here. In summary, If we want to uh, take a transform between rotations and pose, and for a matrix, it's a rotation matrix, and for pose, it's a homogeneous transformation matrix. For a vector, it's q is equal to r into p in terms of rotation. For pose, it's q is equal to h into p, where q here would be a homogeneous form, and p here also would be the homogeneous form. That's the only difference. Sorry for the same notation. This should have been capital Q and capital Phi for the pose vector. For the body frame velocities, we have omega hat b is r transpose r dot, and for pose we have g hat b is h inverse into h dot. Note that the inverse is not the same uh, as the transpose as in terms of the rotation case. For inertial frame velocities, we have omega hat s is r dot into r transpose, and in the pose we have g hat s is h dot into h inverse. So moving velocities between two different frames is given by the equation in the red here, and this is also often called adjoint. Uh, Please try to understand the transformation between velocities and the general rotation matrices and the notations, as these are one of the most important and confusing concepts, but one of the most basic concepts which you would need in order to play around with different sensors on a quad rotor. Uh, as always, if you have any doubts, please feel free to post on Piazza or ask in class. Thank you. Bye.